Thank you for introduction. Um, Let me first introduce myself. I finished after I finished my PhD at University of Tokyo. I spent 2 years at Riken AIP here in the discrete optimization unit led by Dr. Maihara. And after that, I moved to the current company called OMRON SINIC. And my PhD thesis was about discrete optimization for low-level computation tasks, such as scale and segmentation without any learning. That's why I joined the discrete optimization unit at Riken AIP. But during the 2 years and at Riken and after that, I have been working on some coming up with methodologies for integrating physical or algorithmic principles into deep learning based methods. And one study I did at Riken was about physics-based self-supervised learning, focusing on the computer vision problem. And then after that, I worked on some differentiable optimization algorithm, especially path planning, known as A-star algorithm, and which is integrated into neural network and so that we can get benefit from both neural networks and also the power of the optimization algorithms. And recently, I'm working on geometric encoders for crystal structures. And today, I'm going to talk about my recent studies presented at previous years and this year's ICAL. And so let me start my main topics. So the substances in the world are actually 3D point clouds of atoms, and there are many kinds of such substances, such as molecules and proteins and crystals. Molecules are basically a relatively small set of atoms, and the proteins are huge molecules with thousands or 10,000 of atoms, and which are coded as one-dimensional amino acid sequences. But unlike molecules, we here focus on crystals, which consist of an infinite number of atoms with arranged in 3D space with periodicity. So okay, so we talk about crystals, neural networks that takes this kind of structures, and we for that we here use transformers. And transformers are originally proposed for understanding textual context. And so I give some intuitive explanation why transformers can be applied for crystal encoding. So in natural language processing, let's say we have some sentence saying that he runs a company. And because words have the meaning of words can be ambiguous, and it may mean a different say meanings depending on context. So here, runs usually means jogging, but sometimes mean they manage some organization. And here, but at the first, in the first stage, we don't know which meaning it is, but with the self-attention, we can see that company means that it is a business organization. So by stacking the self-attention, that the meaning of runs is resolved that it actually means manage and business organization. But if this company is instead a dog, then the meaning of run can change. So here, the sentence means that he is more like exercising his pet. So as you can see, the words, a meaning of words can change depending on textual context. And this is actually very similar to what we want to do for substance structure analysis. So let's see, for example, we have H2O molecules. And when we use transformers, we prepare atomic tokens that symbolically represent species of atoms in the structures. So we have two hydrogen and one oxygen tokens. And then these atomic tokens are, the state of these tokens evolves through self-attention mechanisms by stacking these layers, and then eventually these tokens transform into some abstract states in the given spatial configuration. So yeah, so here the state of atom can change depending on spatial configuration in the structures, and transformers can be applied to estimate these states of atoms. And these neural networks can be used in many applications. And one immediate application is property prediction. So here we have a structure as an input and give it to the neural network to predict some properties like energy or band gap of the structures. And well, such prediction can be also done by physics simulation, but using neural network, we can predict properties in a much faster way. So it can be used for high throughput screening of materials. And also these property prediction tasks are regarded as basic benchmarks for material encoders. And these encoders typically need a specific property called invariance. And I'm today mainly talk about this property prediction task. But also, these networks can be used to predict the structure from some input. And typical example is generative models. And also we can use, say, given some input, we can find stable structures with, with lower energies. And so we can use them to predict chemical reactions between multiple substances. And basically these for these tasks, we need equivariant networks. And also encoders, material encoders are fundamental when building foundation models or multi-model foundation models. And here we can predict high-level functionalities of materials, or we can visualize the materials space using the learned embedding. So for these two topics, I will, at the end of this talk, I will briefly introduce our recent results from our group. So first, I will want to talk about last year's ICAR's work called crystal former. So crystal, yeah, the material science is a field, a classical field to discover and develop new materials with useful properties and functionalities, such as semiconductors or superconductors or battery materials. And crystal structures are a kind of source code of materials. They are, yeah, they have periodicity, that meaning that they are infinite in size with some with periodicity, and this structure can be described by its minimum repeatable pattern called unit cell. So by repeating this pattern in 3D space, we can recover the crystal structure like shown here. And so in material property prediction, we have a unit cell structure of crystal structure, and then give it to neural network to predict some properties. And as I said, it is useful for material screening and it's useful to accelerate the material development process. And also, these networks are important when building foundation models, multi-model foundation models, taking crystal structures. And basically, these crystal encoders do message passing between atoms. And importantly, these networks have to satisfy some property called SE3 invariance, which means that even if we rotate or translate input structures, the output remain unchanged. And so also, because unit cell have some arbitrariness in its expression, the network needs to be also invariant to the shift of periodic boundary shift of the unit cell. So these two unit cells actually represent the same crystal structures. So that, so yeah, in different from invariance, we also have another important property called equivariant, which means that when input are rotated, then output structure will also be rotated accordingly. But we don't talk about these equivariant networks in these talks. So when applying machine learning techniques for materials, basically, when we have some advances in machine learning, then they are first applied to molecules and then later extended to crystals. So when there appear graph neural networks, they are applied to molecules and extended to crystals. And more recently, transformers are applied to molecules, and later we have some transformer models for crystal structures. But yeah, specifically, this graphomer demonstrated that the use of fully connected self-attention is effective for molecules. But because crystal structures have infinite periodic structures, so whether such dense attention can be applied to crystals is an open question. So that's the problem we tackle here. So to explain the architecture, let's start with the case of molecules. So molecules are finite structures. So say we have n atoms, then the self-attention between these atoms can be written here like this. Here the Q and K and V's are query key and value features linearly projected from input X. And yeah, and here we use two types of position encodings, phi and psi. So these position encoding basically encode relative position between two atoms. And by using a distance to formulate these position encodings, we can ensure that the models are invariant under rotation and translation. So but when extend this formulation to crystal structures, the formulation will be slightly changed because so we have a unit cell with finite atoms, but they are infinitely repeating in 3D space. So we we want to consider interactions between one of each of unit cell atom with all the others in the structures. So basically, we need to add the infinite summation here, which basically represent the periodic shift of unit cell. So n0 is here and n minus 1, minus 2, or n1 represent this shift. So because the state of this atom share the same state with these atoms, so these query key and value features do not depend on the unit cell shift, but positions change depending on the shift of the unit cell. So we need, say, an n here to represent the shift of the position in the position encodings. And this formulation, because we have an infinite summation, it does not usually converge to a finite value. So we formulate this position encoding term to make attention term as a distance decay form. So specifically, it is a Gaussian distance decay function. So these are curves basically showing attention weights. So when target atom is interacting with others in the structures, the attentions decay according to the distance. And so that we can, we can have a formulation that converge in a finite range of unit cell shift. And this formulation, we think that this formulation somehow mimics a physical energy calculation algorithms used in as physical simulations. But we do it in a high-dimensional abstract feature space. So this red part can be interpreted as some interatomic potential function between two atoms. And blue term is basically representing some abstract influence from surrounding atoms Jn to the target atom I. And so here, in fact, the electric potential energy between one and many particles in 3D space can be given as this form. So this is potential function, sum of the potential functions. And so this is, I think, very similar, but our formulation in our self-attention formulation do it in abstract feature space. And although this formulation have infinite summation, this can be performed quite like standard self-attention for finite elements. So by simple linear algebra, we can we can have this form so that we see it seemingly does not have infinite summation, but we have some term alpha and beta, and it has actually these infinite summation here. But once these alpha and betas are computed, we can then just do this computation just like standard self-attention with finite elements. So yeah, we evaluated this method on the material property prediction benchmarks. So it predicts formation energy, band gap, and so on. And interestingly, the proposed method outperforms most of the existing methods consistently in all the tasks, and only competitive to Potnet, which was the state of the art in the last year. The interesting thing is that the proposed method requires much fewer parameters, so it's less than half the size of the existing state-of-the-art models. And also, there is some transformer-based architecture called Matformer, but it's actually, it makes many modifications on the original transformer. But here, our architecture is very simple and closely follows the original transformer architecture. So I think our method can be seen as a kind of standard form of transformer for crystal structures. And one interesting extension of this method is that, so this is our formulation. And one problem is that this infinite summation of Gaussians decay very slowly when the sigma is very large. But we can transform this formulation by applying Fourier transformation to obtain this formulation. So this means that when Gaussians have long tail in real space, these Gaussians actually become short tail Gaussian in Fourier space. So we can efficiently compute long-range interatomic interactions in our self-attention formulation. And we demonstrated this idea by replacing half the self-attention heads of the crystal former with this Fourier space attention, and this is the gel space variant. And well, we didn't get consistent improvements, but for energy above hull, which basically indicate the stability of the structure, so we obtain a huge improvement over state-of-the-art result. So for some tasks, such long-range interactions are very effective. Okay, let's move on to another paper which we presented this year's ICLL. This was done last year by Ito-san, who was an intern from Osaka University, and we worked on this paper for 4 months in the last year. And so basically it's about an extension of crystal former. So in the crystal former, we have this form of self-attention, and there are two types of position encodings. One here is, as I said, it gives a distance decay attention. The other one, which I didn't explain in detail, but here it is actually also encodes a distance into a soft one-hot vector, and then which is linearly projected to obtain some embedding of distance. So both terms are based on distance, and these fully distance-based models are key to ensure the invariance under rotation and translation. But the distance are kind of compressed information than original 3D structure information. So such distance-based models have limited expressive power. And to enhance the model expressivity while maintaining rotation invariance, one approach is to use invariant geometric features. And distance is the most easiest way to achieve this, but it is limited in expressibility. But we can use angles between triplets, but this approach introduces many combinations of three-body interactions in the model. So basically, it is computationally expensive. Another approach is to use, say, equivariant features or using equivariant neural networks because invariance is a special case of equivariance. So invariant networks can be achieved by using equivariant neural networks. But these type of networks have heavy restrictions on the form of nonlinearity. And also they have some limitation in the resolution of angular angular resolutions. And also as a personal opinion, it is very mathematically difficult to understand and implement. But instead, we have some approach called frames. The idea is very simple. We can, so even if inputs are given in arbitrary orientation, we can map them into a canonical representation by standardizing the orientation of the input. And this is done by basically finding some structure-aligned coordinate system, for example, using a PCA. And unlike equilibrium networks, such frame-based approach does not have restriction on the architectural design. And we tackle this approach for crystal structures. But there are some problems because crystals are infinite in size. How can we define a standard orientation for such infinite structures? That's one problem. But yeah, we have unit cells which are finite in size, but unit cells are a kind of artificial representation of crystals. And here we show apparently different unit cell slices, but they actually represent the same crystals. So we have some arbitrariness in the representation of unit cells. And the question is, should we rely on such arbitrary representation when determining standard orientations? And the last question is more fundamental. So what are the frames for? So there are many possible ways to construct the frames, but it is unclear what makes a good frame. And simply, is it enough to simply standardizing the orientation, or is there any other, say, criteria to judge the goodness of the frame construction? So it is, it is not answered in the previous work. So we want to answer these questions in this study. So we rethink the role of frames, and we consider that frames are ultimately used in message passing layers in graph neural networks or transformers. So we want to use this R is relative position in message function to update the state of some atoms. But this relative position are not rotation invariant. So frame can derive invariant representation of relative position, and so that we can use more informative structure information about input crystal structures when designing these message functions. So with this perspective, we propose a concept of dynamic frames. So yeah, in this formulation, W is actually self-attention weights in transformer models. And these weights shows basically which atoms in the structures are actively interacting with this target atom. So these weights can be seen as a kind of mask on the structures. And so in dynamic frames, we means that we dynamically construct a frame for each atom and for each layer so that we can normalize the orientation of local structure represented by self-attention weights. So this is the key idea of this method. And to give some intuitive understanding, I draw some analogy to some existing methods. One is that I think this dynamic frame is similar to normalization layers in deep neural networks. So in neural network, we use normalization layers to adaptively normalize incoming features and then pass them to subsequent linear layers. So here, dynamic frames can better normalize the structure information coming from input structures and then pass it to the message function so that this message function receives better normalized structure information. And also, dynamic frames, I think, are somehow similar to rotation invariant local features used in classical computer vision, such as shift features. So here, image patches are orientation of image patches are rotated according to some, orientation of the image to obtain rotation invariant features. I think these two methods give us some intuition of how dynamic frames works in our method. Basically, when we construct a dynamic frame, we use a point cloud of structures and also weights for these structures to obtain transformation metrics for this target atom I. And we proposed two types of method for frame construction. Now, I don't explain details, but one uses PCA with some self-attention weights to find some principal directions of interactions in the self-attention. The other one is also similar, but which is based on point selection prioritized by weight, and while using some orthogonalization for the frame axis. So basically, in these two methods, we ensure F33 invariance by constraining frame matrix to be a rotation. And by using these dynamic frames, we developed a new architecture called the Crystal Framer, which is a simple extension of Crystal Former. And its self-attention is, as I explained, it can be formulated like this. And for this position encoding, we use distance-based some embedding term. Then we also here add a term based on dynamic frames. It basically uses relative direction vector, 3D direction vector that is projected onto the frame axis. And so we have one value for one axis of the frame. So we have three such terms here to increase the uh, expressive power of the crystal former. And we evaluated this method and on some benchmarks. And here we use crystal former as a baseline model, and also use several types of frames. And the last two rows shows the results of our dynamic frames. And basically, we by using frames, we obtain very big improvement from here to here. And also these these PCA frames are static counterpart of weighted PCM frames, and also the static local frames are counterpart of proposed max frames, and basically these results show that dynamic frames outperform conventional static counterpart method. So that's it. So okay, let me finally introduce some other studies in our group. The one is about the decoding of materials. Point clouds are popular format of 3D structures in computer vision also, but in computer vision, point clouds are kind of samples of dense surfaces. So the number of points actually doesn't matter in these structures, but in atomic systems, the number of atoms is very important. And when decoding such structures, these numbers are unknown and also a variable. And so this makes very challenging to decode atomic system structures. And here we propose to present these point-based structures as continuous vector fields. Here, F is a neural network, and P is some 3D query point, which is given arbitrarily, and Z is a latent vector of a structure that we want to represent by this network. And for the output tells us some information about atom that is closest to the query atom. So one type of information is the 3D displacement vector, which means that when we give a query point here and when the true position of the atom is here, then the network output this displacement vector so that we can know where the true position of the atom is. And also, this output S can be a categorical distribution of atomic species, so that it tells us whether the nearest atom is hydrogen or helium or oxygen also. So, and we use this field-based approach to develop crystal autoencoders. So as autoencoder, we have input structures and then convert them into some latent vector. And from latent vector, we recover original input structure using the proposed decoder networks. And we all compared this approach with existing voxel-based decoder. And as you can see, the proposed field-based approach can more accurately recover the original input structures than voxel-based approach. And this approach shows the errors, the signed errors of number of atoms in the recovered structures. So if it's here, it means that the recovered structures has too many atoms, and when here the method failed to recover some atoms, and we found that voxel-based method tend to fail to reconstruct some atoms, while our method better reconstruct the structures. Okay, so this is the last study I want to introduce. It's about clip-like multimodal learning for materials science. In computer vision, the community has fostered large-scale data set of images with textual annotations, such as ImageNet and MS-COCO. And these data sets are basically enabled us to develop multimodal foundation models that align text and images in the same embedding space. And prominent work is, as you know, the CLIP by OpenAI. But in material science, we don't have such large-scale resources. And this is because annotating crystal structure, it requires expert knowledge, and crowdsourcing such annotation is basically infeasible. So instead, we leverage a database, or a large-scale database of materials with publication metadata, such as paper titles and abstracts, to enable such constructive learning between text and structures. So we, as a data set, we have a pairs of structures and it's the paper information. And basically, in the pre-training stage, we map, we encode paper title and also encode crystal structure to align them in their embedding space. And one application of this method is text-based retrieval of crystal structures. And here we show ROC curves of retrieval performance, showing that going upper left it means better performance. And the key finding here is that the proposed literature-driven learning actually enables models to predict high-level functionality of crystal structures like superconductivity. So this this line shows the ROC curve of superconductors, which was very successful. And another application is that we can visualize the material space in some intuitive way. So here we show TSNE visualization of the resulting embedding space, and we can see that structures with similar properties automatically form clusters in this embedding space. And here we also show the predicted band gap of structures mapped in the embedding space. And as you can see, materials with similar band gaps tend to form clusters here. Yeah, okay, let's summarize my talk. So first I introduced crystal former, which is a natural extension of standard transformers for periodic crystal structures. The key idea is to use distance-taking attention that abstractly mimics energy calculations in physics. And also we can extend this model to use Fourier space attention that is useful for capturing a long-range interatomic interactions. And we extended this model by introducing dynamic frames which are derived from attention mechanisms, so that we can enhance the expressive power. The application of these networks is that they are immediately applicable to property predictions, and also important in embedding learning and multimodal foundation models. And in the future, it is interesting to extend these invariant networks to equivariant networks, which enables the structure prediction and force field prediction. And these networks are essential for generative models such as diffusion models. Okay, thank you for your listening.
Thank you, speaker. One comment from chat.
The way you use the crystal to create a data from recently some text-based representation. For organic substances like drugs, there's some textual format of structures called the smiles, and I heard that they are very successful in such type of substances, but unfortunately for crystal structures, for now, there are no such effective textual representation of structures, and I personally, because I believe in geometries, I think the geometric approach is the only promising way to accurately understand the crystal structures, I think. And
thank you very much.
yes, the thing is materials to string-based presentation. What's Yeah, I think I answered the question that we have for now. And I'd like to hear any question if any of the audience.
Question. Common issue with the transformer is that the computational time scale is the squares of the length of the text. In this case, squares of the number of atoms or unit cells. Does it become a program when using transformer to predict crystal structure?
Yes, basically, yes, but that depends on how we implement. Most of the existing crystal encoders uses some neighborhood structures like KNN or radius-based nearest neighbors to define the nodes of say key and values, nodes of neighbors. But so if we use that formulation, we can. It's just the computational order is nk, so that it is basically less than square of n. But in current formulation, implementation of crystal former, it is actually n square, and so it becomes slow for large structures, and when in our tested data set, well, one data set has on average 10 atoms per unit cell. Another one has 30 atoms per unit cell, and that is currently some kind of practical limitation with this current implementation.
Okay. Is there any question for me? Another question for why can Christopher achieve higher accuracy with fewer parameters? Is there any intuitive explanation?
Yeah, I think the reason is that is basically here. Because the model of the crystal former exploits a strong inductive bias that is by mimicking the formulation that is typically used in physics simulations. So that I believe that this model is doing some good computation.
Thank you. Is there any one question? Oh, one question for me. If you will check.
Okay, transformers are also widely used in generative tasks. May I ask whether the pseudo-finite periodic attention in your crystal formers can also be applied to transformer decoders for generative tasks? Yes, I think that depends on which generative approach we use. But for example, in diffusion-based models, basically, in such approach, in each backward step, we are given some noisy structures and then the noise output the denoised one, so that and so in that form we can use our architecture if we extended it to equivariant models. So yeah, so to answer the question, because the current model is based on invariant models, so it cannot be directly applied to generative tasks because generative tasks often require equivariant networks. But if we extend our model to equivariant version, then I think our architecture can be used in such generative approaches.
Thank you very much.
Thank you.